In standard computational chemistry, our baseline is the Hartree-Fock method. It relies on a mean field approximation to make complex mathematics solvable. This model assumes an average crowd behavior. It treats each individual electron as if it only reacts to a smoothed-out average field generated by all the other electrons in the system. This diagram shows the physical flaw in the Hartree-Fock view. On the left, we see the average field, a smooth concentric gradient. The reality, on the right, is more reactive. Electrons repel each other instantaneously, based on exact proximity, not an average distribution. This moment-by-moment short-range avoidance is the crucial physics missing from the Hartree-Fock model. We call it electron correlation. Relying strictly on an average field ignores the localized instantaneous reality of quantum repulsion. The challenge is that electron correlation is not a single monolithic variable that can be fixed with one simple equation. This chart illustrates that the missing physics splits into two entirely different physical phenomena. The path divides into dynamic correlation in blue and static correlation in yellow. Because these two phenomena differ in their quantum origins, they require completely different computational methods to solve. Treating correlation as one generic problem produces physically invalid results. Dynamic correlation is the instantaneous, localized dance where electrons actively avoid close contact within a single, stable, overarching state. Consider the physical analogy in this visual. Two people walking down a hallway intend to follow an average path, shown by the straight dotted line. However, they make sharp vector shifts, highlighted in blue, to avoid close contact the moment someone steps directly into their immediate personal space. In the helium atom diagram, Hartree-Fock places electrons in a symmetrical average state. But reality shows if one electron nears the nucleus, the other is forced elsewhere. This rapid spatial adjustment around a stable state is dynamic correlation. It is the fine-tuning of electron positions within an already accurate electronic picture. To capture this mathematically, we rely on a specific logic. The system possesses one clear, dominant identity, represented by a single Slater determinant. Looking at the math in the left panel, the actual wave function can be highly approximated by taking this main determinant, the large phi naught square, and perturbatively adding numerous tiny corrections, shown here as small blue particles. This single reference logic forms the foundation for standard computational methods like MP2, CCSD, and standard DFT. Single reference methods successfully capture dynamic correlation because they only need to calculate minor deviations from one highly reliable baseline. But there is a critical limitation to these single reference methods. They fail when a single electronic configuration is no longer sufficient to describe the molecule. Take the simple H2 molecule. At its equilibrium bond distance, the system is well described by a single bonding orbital configuration. As the bond is stretched toward dissociation, the physical reality shifts. The bonding and antibonding orbitals become nearly degenerate, meaning they are very close in energy. This graph tracks the stretched H2 bond. Forcing a single determinant here enters the danger zone, predicting absurd ionic dissociation into H+ and H-. Physical reality demands neutral hydrogen atoms, mathematically requiring us to mix both configurations equally. When molecular orbitals become nearly degenerate, forcing a single average picture creates physically impossible results. This requirement introduces static correlation, the condition where a molecule exists as multiple, competing electronic arrangements simultaneously from the very start. This coefficient histogram visualizes the mathematical weight of the configurations. Under static correlation on the right, two or more determinants carry nearly equal coefficients. This photograph metaphor highlights the distinction. Dynamic correlation adds high-definition details to one main picture. Static correlation means the molecule requires multiple distinct photos to represent its reality at once, mandating multi-reference mathematical methods like CAS-SCSF. Static correlation represents a fundamental tearing of the molecule's identity between multiple major states. The primary challenge for a computational chemist is diagnosing the molecule's state to select the correct mathematical tool before running an expensive calculation. It all hinges on one definitive diagnostic question. Is there one obvious electron configuration that dominates? This flowchart maps the decision process. If one configuration clearly dominates, follow the blue pathway. The main missing effect is dynamic correlation, and standard single reference methods are safe. But if multiple configurations seem equally reasonable, take the yellow pathway. You must switch to multi-reference methods. Failing to properly diagnose the molecule's fundamental state before beginning a calculation ensures the failure of the theoretical model. Ultimately, dynamic correlation represents the localized, evasive maneuvering of electrons within a single, stable framework. This final synthesis outlines the core contrast. Dynamic correlation acts within one main electronic picture, while static correlation requires overlapping multiple fundamental frameworks to capture a torn molecular identity.